Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to tonight's Contemporary Science Issues and Innovation program featuring Sanjoy Mahajan. Dr. Mahajan is Visiting Associate Professor of Electrical Engineering and Computer Science at the Massachusetts Institute of Technology and an Associate Professor of Applied Science and Engineering at Olin College of Engineering. Dr. Mahajan took his undergraduate degrees in mathematics from Oxford and physics from Stanford, and he received his PhD in theoretical physics from Caltech in 1998. He became a founding member and the first curriculum director of the African Institute for Mathematical Sciences in Cape Town, South Africa. Later, he joined the faculty of Olin College of Engineering, and he was also associate director of the Teaching and Learning Laboratory at MIT. Dr. Mahajan is very much committed to improving mathematical training of science and engineering students especially, and beyond that to including intuitive techniques in mathematical education in general. He would be the first to say this is not some version of the new math. Rather, he wants people to learn the importance of guessing and trusting a hunch in the process of solving a problem. That's what scientists often start with. Too much rigor, he says, leads to rigor mortis. We urge you to see his very popular TEDx talk at Caltech about all of this. The links are on our event page for tonight on the Science for the Public website. Dr. Mahajan has produced 2 textbooks, both published by MIT Press, demonstrating the intuitive approach to mathematics. I'd like to point out that both are available, of course, in print, but also online under a Creative Commons non-commercial share-alike license. We're very honored to welcome Sanjoy Mahajan. Welcome. So I'd like to get your input about mathematics generally to start with. Most people think it's way too hard, at least in this country, and that also it's for engineering and science, but not for the rest of the world. What's your take on that, please?
I think mathematics is as important as language. It is a language, yeah. And it's the language in which we live so much of our modern society. And it's one reason historians have actually looked into this. Why is it that mathematics is so important, and numbers in particular? And strangely enough, it's because we have democracy and we have a large country. And so it turns out that as societies grow in size and in democratic nature, they need numbers more and more, which seems a bit strange. Well, why would that be?
Yeah.
And what it seems to be is that in a small, elite-governed society, you don't need numbers. You just have the elites in a back room cutting all their deals. Say, think of England in the 1700s, right, 1800s, sure, or even a lot of the 1900s. But as the society becomes more democratic, you need some way of having a universal trust that people can look to, because they say, oh, well, just talk. Well, that's just your opinion, and that's just my opinion. How can we find a way of building consensus across a whole bunch of different opinions? And it seems like numbers are one of those ways that people trust across a wide spectrum of ideas and opinions. And so numbers become more and more important as we become more democratic and larger. So America is the society which numbers are the most important, and sadly, one of the worst in terms of education about mathematics.
Yes.
So the gap is huge.
Yeah, and compared even to other developed nations, that there's this problem here, but we can come back to it. But you have this great mathematics background yourself. What does mathematics bring to life, apart from this need in the practical world today? But a lot of people, especially from mathematics, say, no, this is a window to reality. And what's your take?
Yeah, mathematics is like the connective tissue that links together the world. It makes no sense without mathematics. The patterns in the world, the why do things fall, how do they fall, how do they move, the social world, that's the physical world, the social world, the flows in the social world, money moving around, resources, all of that, there's mathematical constraints on it. If you put something, if it moves at some speed and it moves for a certain time, it gets only so far. It can't get 10 times as far. So mathematics in some way is reality coming home to roost.
Yes.
And that's one reason I think, in my cynical moments, why we don't like mathematics, because we're not a very reality-focused society.
Oh, that's an interesting thing to say.
We don't want constraints. We want to live like children.
Yes, that's rather interesting. But do you think that's true of other cultures?
Well, I think other developed societies actually live with reality more. They say, for example, we don't have an infinite amount of oil. We need to have public transit. Whereas we say, let's just tear up all the train lines and build more cars and defend the American way of living.
Exactly. So you could say that we have a very irrational...
We're not reality-focused.
Perspective, perhaps. But on the other hand, you can't operate a modern economy or anything else anymore without the mathematics. But I was wondering...
Seeing that now.
I was just wondering if you see nature, for instance, differently because of your background.
I don't think I can't even understand nature without it. For example, a blue sky. You know, what is a blue sky? Why is it blue? Well, it turns out that the reason it's blue is that there are springs all over the sky. So where are these springs? And the springs, they're not actual little mini springs, but they're the bonds between the electrons and protons in every air molecule or nitrogen. And so why is that a spring? Well, mathematically, it behaves like a spring. So when the sunlight comes and it wiggles the electron, it wiggles just like it was attached to the proton by a spring. And so in the atom, you have this spring vibrating up and down, and then that spring itself gives off light. And so that light we're seeing is the light from all these little springs that are being shaken up and down, each one a little radio antenna or a light antenna. And so why is that a spring? Well, it has the same mathematics as the springs you know as slinkies. And so you can understand it in the same way. And without mathematics, it looks like a completely different thing, which makes no sense at all.
So you get insight immediately just because of knowing this. And
you see the connections in the world.
Exactly. That was one of the things that I think scientists say right away. You see patterns. You couldn't do it otherwise. You wouldn't see patterns. You wouldn't see connections.
And you'd also, you overflow your mental registers. So you only have 7 or 8, say, slots in your short-term memory to think with. And then after that, it just gets overflowed, and then you can't actually think anymore. And so if you look around in the world and you see thousands of different little itty-bitty things with no connection, it can't make any sense. You have to find ways of connecting it, and one of the ways is through mathematics.
That's interesting because it seems as though the brain moves toward that. Actually, that may be a very fundamental part of human brain, because it's making patterns is so important.
It's the only way to survive.
Right. In your 2 books, you give a lot of attention to problem solving because they're designed to help engineers and scientists think a little differently. When you say, intuition and guessing and going with your hunches, this is very different from the way engineers and scientists are trained. And so how does that approach benefit scientists and engineers to start with?
Well, it benefits them because so much math education is, to put it mildly, a big fat lie. So what you see in most math courses is, here's a formula or here's a proof. And no one ever tells you, what problem were people trying to solve? Why did they think this even might be true? What ideas would you use to check whether it's really true? So the whole construction of this house, you never see. All you see is the completed house. And then you tell students, all right, well now go make your own house. Oh, you don't think you can do that? Oh, you can't make a perfect house on the first try? Well, you just must not be good at math.
You're not.
and so what we do is we cheat the students instead of actually showing them how the house is built and showing them the guts of the construction, where you think, well, first of all, where am I going to build a house? How big is it going to be? How many levels is it going to have? All of that into where you have to actually think and plan and guess and even make assumptions. We don't tell them any of that. We just show them the finished product. And then we look like wizards. And so it's very good for the egos of the teachers, but it's very bad for the egos of the students.
I can't resist asking, you know, the great accomplishments in both engineering and structure, architecture from ancient times, like the Peruvian walls, the Incan walls with no cement or anything, and people figuring this stuff out and building enormous buildings that are architecturally very complex and so on, but they didn't have this kind of education.
Well, some of them had some of this education, actually. So in the temples, there was pretty thorough education.
Oh, okay. So they were teaching something or other
there.
Yeah,
so many mathematical ideas were developed actually to do these kind of constructions.
Okay. Do you think that's true worldwide? I mean, you know, that people were aware of geometries and things like that, but what I meant was you didn't have these little textbooks to show you how to
and
do
so
things.
Actually we didn't teach people fear of math either.
Well, that's a question.
which is what we do now, because now what we do is we teach people, well, in math is in language, there's many ways to express yourself. You say, okay, well, write your essay and the way you think best captures what you want to say and will convince people. So that's a creative process, and there's lots of freedom in there. But with math, all of a sudden we tell them, okay, here's your problem, here's the one answer. And we teach people there's one way to get from the problem to the answer. And that kind of teaching actually produces terror in people. They think, okay, I'm here on this one mountain peak and I have to get to this other mountain peak, and there's this valley, this mountain pass I have to cross over, and if I make one mistake, I'll fall into the valley of error below to my death. Yeah. And of course you're going to have math anxiety and math phobia with that kind of teaching.
Do these engineering and science students that you work with, and you work with the cream of the crop, do they have the same thing, a foreboding of disaster if it isn't exactly precise? Is that true? So there is
even
a kind of anxiety. That's
even
interesting.
more so. So they've developed more armor plating. So they've actually developed that in more areas of mathematics. So they've taken subject X and Y and Z. Yeah. And in each of those, they've learned that way of thinking. And so then what happens is something new comes along, like an actual problem, and they say, oh, I never took a course in that. And you say, well, of course not. The idea isn't to take a course in every single problem that you might have. It's to find ways of thinking that you're ready to use for any problem. And that requires the flexibility. And so if you're fearful, just in your own personal relations, if you're scared or worried, you become less flexible, or you become more rigid.
Exactly.
And so that's what happens to the
students.
students.
So it becomes defensive. It's an intellectual defensiveness in this case, though.
That's right.
It's almost wonderful to hear that they're terrified.
They're terrified.
Because they do pretty well in the end.
So what I find in my courses is the older the students are, and when I try to teach approximation and guessing and inexact answers and getting away from rigor, because it leads to rigor mortis, is that the older the students are, the harder time they have with it.
Because they came up with a different system altogether.
And they've done so well. So at each stage, they're filtered. Okay, if you did really well in high school, you get to go to MIT or Cambridge or Caltech. If you do really well at MIT, you get to go be a grad student.
Right.
So they've done really well with the regular system.
Right.
And so we've filtered for the people who've done so well with it. You don't want to change that. That's risky.
Yes, right. And how do they react? Because you work with these students and turn them sort of upside down in the process. And I'm thinking of a couple of reviews of the book by mathematicians and engineers who said, oh, this just changed my thinking. I had to work at it, but it changed my thinking. And I wonder how the students react.
Well, I find what I have to do is I have to be very unsubtle about it. So I give them problems that they think they should be able to solve. Like, okay, why is the sky blue? They've taken the physics of springs, they've taken all the physics to do that kind of question, but they never put those things together in with ways of thinking that would allow them to answer it. And then they realize, oh, wait a minute, even though I know all these little pieces, there's some big picture that I'm missing. And in some ways I'm a little unkind and I rub their noses in the dirt just to show them that, hey, it's not your fault. You're bright and you're curious, but you just learned the wrong things and you've learned the wrong way of thinking. And so you need to learn other ways of thinking so that you can solve new problems and not just solve problems that you've already seen before or that are similar to what you've already seen before. So that's the way I try to get them to change their thinking.
Do you see a big result after this kind of progression, once they get through this barrier, that they have a different mindset?
Yeah, I've gotten nice letters from students after they graduate or go on to other courses or other jobs, and they say, oh yeah, that was so useful. I was, on this project, and it seemed like it was going to take months and months, and then I said, wait a minute, let me just use my street fighting approach here and figure out what's the one main problem in this program and just solve that. And then, the thing ran 10 times faster and my whole problem was solved. And then I had 2 months where the boss just let me do whatever I want because they were ready to spend 3 months on that project.
Right.
And so I'm very happy when I hear things like that.
Of course.
I say, oh, okay, somebody actually used this in their research. And then also I ask the students to just give me examples of whenever you use these ideas.
Yes.
And so some of them just say, oh yeah, I managed to impress my girlfriend or boyfriend
doing
doing quich calculations, which they never thought they could before.
Yes.
And so I think, okay, well, that's a good use.
That's
as well.
a very good use.
Yeah.
Take it out to society.
But I think maybe my favorite of all was one time. This was in Cambridge, and we'd invited England. We'd invited all the physics students to dinner. With the physics professors. And so there was 2 or 3 of us with about 20 of our students, and we were sitting on the table at 2 different ends, and then all of a sudden at my end of the table we were chatting away, and then this English sponge pudding from heck, let's just say, came over to the table, and they said, what do you get for the stiffness of this pudding? Which the stiffness is how much how springy it is, or how much it resists being pushed. They said, we measured it, but we're curious what you get. So so we tried it, we measured it, we put spoons on it and tried to figure out how bouncy it was, and we compared numbers. And so we spent, good fraction of the dinner discussing
the great minds really have worked on sponge cake then. Good.
And of course you couldn't eat it because
no,
it was
of course
totally
not,
inedible.
not after that.
Well, even before.
Oh,
so,
I see.
So this was a good use of it. But I was happy to see them taking these ideas of, okay, we don't have to have the exact springiness of Jell-O. It's not even clear how you'd measure that. Right. But we can just use it in our everyday life.
Right. Speaking of everyday life, not quite, but it seems as though, certainly in science, I'm not sure whether it's true in engineering, but in science, people do have to make guesses simply because you don't have the facts at hand. So at the theoretical level, which you came out of this in physics, then it seems necessary. Is there less fear with people with that kind of, or people in science, like in theoretical areas of science?
So that's the interesting part, is that people who do these professionally, they've found one way or another, even if their education didn't teach it to them, they've found some way to make guesses. So either they didn't find that way and they left doing science, or they found some way and they stayed in it. And that's maybe even more true with engineering. And so all the people who are doing these fields say, oh yeah, this is exactly what we should be teaching our students. When I ask people, what frustrates you about students, about what they learn after our degree course? They say, well, the thing that frustrates me most is the students will do a calculation and they'll come up with absolute nonsense and they'll just write it down because it came out of their calculator.
Ah, yes.
Without thinking, does this number make any sense?
Yes.
Is it even reasonable that the universe could be, 10 to the 25 seconds, old?
Yeah.
That seems crazy.
Yes.
Or that, the mass of a car could be 10 million kilograms. If you write that down, you really don't have a feel what a car is or a kilogram. And so when students do that, you realize, well, they may have gotten all the problems right, but we've somehow failed to teach them something important.
You how to think.
How to really have a feel for how the world's put together.
And
use numbers to actually measure the world.
Yeah.
And so, my colleagues and scientists, engineers around the world, they say, this is so important to teach people, but somehow we just haven't managed to teach it to them.
Now, engineering students, probably especially, apparently gripe a lot that a lot of the math courses they did take don't seem to help them.
No, they don't.
And that's sort of your main point there. Why is this happening?
It's because, the math courses are taught by people for whom math is a thing in itself. which, you know,
religion.
Religion or thing of beauty just for its own sake.
Right.
And there's people in every field like that. There's artists who just do art purely for art's sake. There's people who write just purely for writing, not necessarily to express to other people what they're saying. And I think that's fine, but those shouldn't be the people who teach writing or teach art or teach math to other people who need to use math. Because they have a completely different way of looking at it. And so when you take a math course, say as an engineer, if you take it from the math department, usually they'll teach you how a mathematician thinks, which is, okay, here's...
And there's the difference.
And and the mathematicians have this culture of kicking away the scaffolding, which is, okay, here's a proof, here's a theorem, here's a proof, but no idea of the guesswork that went into why did we even think of this theorem? Why would we think this might even be remotely true? Why would we even care about it? None of that happens. And so I remember when I was an undergrad, I used to torment the math grad students by just I would ask them, well, so what are you working on for your PhD? Because I was curious. And they would tell me something, and I usually wouldn't understand it very well. I would understand some of the words, but then I'd say, can you give me an example? And they would look at me like I came from outer space. We haven't got to that. And so
we haven't gotten to it.
So we're not even, they're not even thinking in that way. But if you're going to use mathematics to understand the world, the world is one big example. You know, if you can't find an example, you're not looking at the world.
So once you introduce this to students, they sort of change their mindset and they can move on. But you brought up an interesting point, is that there seems to be a divide between the way mathematicians think and the way engineers think, but still even, as you say, students in engineering take their courses from mathematicians, and that is they might get misled that way, but even so, they sometimes feel frustrated that whatever it is they're learning in this package is not somehow applicable to the kinds of things they need to solve. Do you agree with that?
And what I find is after they come out of most of the math courses, they can't actually solve problems that require any kind of creative use of mathematics. You know, they're really good at doing long chains of algebra. That doesn't really mean they understand what's going to happen.
In spite of this deficiency in the curriculum, they have accomplished tremendous things. Some of the accomplishments in the last, say, 50 years are amazing.
But you only need a small fraction of people to be able to really understand what's going on to do that. And what I'd really like to see is that fraction become not so small. So that most of the society understands how to use mathematics.
And that's really the next thing. This is that this does seem to be an elite all the time. We are, I think, rather consciously raised to believe that in this country, at least. I have discovered elsewhere that's not the case.
And so here in this country, we actually believe math is an inborn talent.
That's another thing.
It's a gift. Either you have it or you don't.
I
mean, I remember when I was a kid in school, you know, obviously I was good at math then too, and people would say, oh yeah, all Indians are good at math. You know, so it was just because I was born with it.
So it's another genetic thing there.
No, actually I liked it from young, and I worked at it and I thought about it a lot, and that's how you get good at math. You use it, you try it out, you play with it. That's how you get good at anything. But you weren't afraid
of it.
And so if you think of it as a skill, you know, no one thinks, oh, you're just born being able to play basketball. Everyone realizes you need to have a basketball coach, or swimming. You have to be taught how to swim. Or you're just born knowing how to ride a bike well. No, you have to be taught this. But we think crazily for mathematics, it's some inborn ability. Either you have it or you don't, which is very convenient for teaching, because that means you don't have to teach. But you know, it means we should actually think, we have all this research now on expert performance, what makes expertise. We should just use that for math teaching as well.
You talk about these various kinds of tools, you know, in the one book, Street Fighting book, but can you give us some ideas about things that ideas you would employ for everyday use for people, ordinary mortals?
So for most people, I think what goes wrong in their mathematics education is that math becomes meaningless. So numbers don't have any meaning. So in fact, you can almost see it if people are reading an article which has numbers in it. You can just replace every number with vague grunting noise, and that's pretty much how people hear the article. So, And that's terrible, because what that means is politicians and charlatans of various stripes can produce all kinds of schemes and tell people lies and just basically bamboozle them into doing things that are against their own interest.
That's right.
So what you have, the first step is you have to start giving meaning to numbers. And the only way to make meaning of things is you have to connect them to other things you understand. So you first have to start connecting numbers to other numbers. I mean, this is just almost basic knowledge of friendship. How do you get people together? Is they have to have connections and become friends with each other. Well, same thing with numbers. You have to get numbers to be friends with each other, and you have to make friends with numbers. So the first most important tool is comparison. Every time you see a number, compare it to something else. So I'll give you an example. So I read in one of the Boston papers, maybe a couple years ago, there was Stanley Cup was happening, or the Stanley Cup was won, or something like that. And this was around, in Boston. So the newspaper said, and 1 million cheering fans filled the streets near North Station, or wherever the stadium was, to celebrate the Stanley Cup coming home. Now, okay, so now normally you see the 1 million and you think, okay, grunt, ignore the number. But let's actually say, okay, we're going to try to make friends with that number and compare it, and to see whether the number is reasonable. So 1 million. Well, what other things are described by numbers of sort of that size that are related? One is the population of Boston and all the surrounding towns, which is 1 million. So what they're saying
everybody
is
got out in the
everybody
street.
from Boston and the surrounding towns came to North Station, to the
Lie number one.
Right. So you realize, okay, so once you compare it, you realize, that number is just bogus. And so that's the fundamental tool, is to start comparing numbers and always do things by comparison. Oh, that's 2 times bigger. That's 1/2 as small. That's 3 times bigger. Oh, that's 100 times bigger, but it's for example, murder rates or traffic accident rates. So you'll always see them given as just simply a straight number. There was X thousand, say 30,000 traffic deaths in the US, and there's maybe 3,000 traffic deaths in the UK, let's say. I think that's roughly right. The question is, let's give meaning to these numbers. You can't just compare them just like that, because there's a different number of people in the US and the UK. So the comparison is, well, in the US, there's 10 times as many people, 5 times as many people in the US as the UK. But like say 10 times the traffic deaths. So the US is twice as dangerous on the roads as the UK. So then you have some meaning to these numbers. You started to connect them into a link and say, okay, factor of 10 in traffic deaths, factor of 5 in population. Now, I don't remember exactly if those are the numbers, but I think they're close, the traffic death numbers.
But the important thing is that comparison.
You always do that comparison.
Right.
And so when you first start doing it, just like when you first start you go to a new cocktail party, and you feel a bit awkward, you don't really know people that well, but you start to make friends with people and start to chat and build a connection. Well, the same thing, these numbers, you'll start to make friends. You'll say, oh, that's what 1 million is, or that's what 1 billion means, or these, and so the numbers in the world around you will start to make sense. So that's the first broad group of reasoning tool you need to master numbers. I
can't resist here that if you did that, you would not be so easily misled by media nonsense. So think of, all these demonstrators or this or that or troops or anything you like, but you're given a good bit of misinformation along with the information. This would be quite a good check. So it trains you in a broader way than just in mathematics.
That's right. You get a good BS, you develop a good BS detector.
Exactly.
And then you start to look for comparison numbers. Like one of my favorites is to look at demonstrations and see the total number of demonstrations. So there's all these claims of how many
and they
people
all
were
vary.
there. They all vary. And so what I find is that when the demonstration supports whatever the government is doing, so if they're bombing, if they're bombing somebody who's quote bad, who we are supposed to think is bad, and there's a pro-war demonstration, then the police will overcount the demonstration size. And if we're bombing somebody who was, and it's an anti-war demonstration, we're supposed to like the bombing, then the police always undercount. And you can start to look at those factors, factor of 2 here, factor of 5 there. And so now you're making comparisons and not just seeing random numbers out there.
That underscores what you said about a democracy, that you are much more fit to be participating in a democracy. It almost demands it.
You need it to be a citizen.
Exactly.
Which is why I think math education is so bad here. That's so in my cynical moments, I say, well, okay, so America has in some ways the most formal amount of democracy.
Yeah.
So we had universal suffrage,
Yeah.
or universal suffrage among the earliest, and the least property qualifications among other societies. So then you need some way to make sure people, okay, if they have some control over the society, you have to make sure they're too stupid to use it.
Yes.
So let's just make sure they don't understand anything about numbers.
Yes.
But so then, once you have the tool of comparison, now what you'll find is that there are all these numbers out there, and they start having meaning to you. Before, they were meaningless, so they just sort of swish by you, and you could just ignore them happily.
Right.
Now they're coming at you, and they have meaning, so they hook onto you, so they overwhelm you. So you need to then do one more thing, because if there's too many things coming at you that you have meaning, so you want to grab them, you get overwhelmed. So to solve that problem, you need to actually throw away information. You need to approximate. So there's basically two things you need to do. You need to give meaning to stuff, and then you need to throw away the extra information that you don't need. So I can give you an example of what happens if you don't do that. You get lost in the details. I asked students to estimate the health budget of the United States. So how much do we spend every year on healthcare? And so the student, she did actually quite a good estimate. She said, well, there's insurance premium per person is something like 5,000 or 10,000, and there's say 300 million people. So that's something like a couple $1 trillion or $1.5 trillion, let's say. I think she got $2 trillion. And then she said, oh, but we have to also think about the cost of prescription drugs. And then she did it, okay, each person, blah, blah, and got something like 100 billion or whatever it was. And then she said, okay, it's 1.5 trillion and 112 billion.
That's the war budget, okay?
Yeah. But that's crazy, because the 1.5 trillion is pretty inexact. Yeah. And there's no point actually going and making such an exact calculation of the prescription drug.
That's your real,
So you're actually wasting your effort and cluttering your head up with noise. So make your approximation, move on.
This is almost counter to everything we've all learned, at least in my generation. Certainly you'd be so careful and rather detail-oriented, and you're saying, no, you've got to get past this, you go in. Is your idea to replace completely the way we teach math, or is your idea complementary? That is, you're not throwing out accuracy or whatever.
What I want to do is turn it on its head. So what happens is now we do accuracy, 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 accuracy.
And detail.
Detail. Sig figs is the mantra everyone learns in schools. How many significant figures? And you learn all these rules for if you have 3 significant figures, after the decimal point, or 2.722, and you combine it with this other number, how many significant figures you have. So people get anal retentive about all that. And so you learn that, and then you drive out most of the students. And the ones who survive into graduate school, maybe as postdocs, and become faculty, there they learn how to approximate and think intuitively.
so late.
It's too late, and it's only 0.01% of the population.
Yeah,
so I want to turn it upside down and say, okay, let's actually do things roughly first.
Yeah.
So, and then as we get more and more need for accuracy, we build in more and more accuracy. As you get more and more mathematical tools, you can use differential equations, you can do more and more things. Then you get more and more accurate as you need it. But the first things in how you approach any problem first should be rough, approximate. What's your feel? Is it, if you can't tell whether it's millions or billions, you shouldn't actually be getting out your calculator. Because that's not going to solve that problem. So an example of that, actually, this is actually with my daughter. She was, I think, 4 or 5 then. She said, Daddy, how long is that couch over there? And before I could answer, she said, 60 feet. Now, I don't know if you know Cambridge apartments, but certainly not any Cambridge apartment we live could fit a 60-foot couch in. So I realized, okay, she doesn't have an idea, A, what foot means and what 60 means. So I said, okay, we're going to measure this in units of Elsa. Her name's Elsa, which everyone now thinks we changed her name because of Frozen. But that was actually her name long before Frozen came out. So I said, okay, Elsa, we're going to use you as the measuring rod. So here, she must have been 4 then, because I could still do this. I said, okay, lie down on my arms. And we just used her to measure the couch. Okay, there was 1, 2...
1 body, 2 body, 3 bodies.
I think there was 3 Elsas to make up the couch. And so then she had an idea, okay, I don't care whether it's 2.5 or 3.5 or 3. Roughly 3 of her is the couch. And so always getting that feel for everything you do.
But all the other thing is just connecting this, the numbers a lot. I
to
can just
body.
See. And also to make general things, which is very much a part of a creative process, whether it's scientific or artistic or anything else. So I need to close up, it looks like, so that you can talk to the audience
sure.
here a bit. But I think we can say at this point, you think most people could really learn a lot higher level mathematics than they do learn.
I think they could have a much deeper understanding of how numbers fit and underlie our world, just like they have about language.
Yeah. Right, and it's a lot of the same principles apply probably. And would you would restructure mathematics for sure from the ground up? Is there any nation that you think everybody's complaining anymore because we're global and we need to change? Everybody needs to change. Do you see anything as exemplary or even close in terms of this kind of education?
Yeah, there was an example in Manchester, New Hampshire.
New Hampshire?
Yeah. So Manchester, New Hampshire had the best mathematics curriculum I think the world ever had. So the superintendent of schools said the math teaching is, and this is his words, chloroforming our students' reasoning ability. So what we're going to do is we're going to stop the formal teaching of arithmetic and teach students to approximate, estimate, have a feel for numbers, and then teach them all the formal algorithms in 7th grade. So they learn long multiplication, division then. And so this he did very successfully from 1924 to 1938.
So this was way back.
Yeah, and he's brilliant. So Louis Benezet was his name. And it's, I think, one of the best math curriculums the world has ever seen. And he was driven out by let's call them the standardistas, the testing maniacs.
Yeah, even then.
Even then, they were the...
Yeah.
But that was an exemplary model.
And so that's your approach would be much more along those lines, which is a real discovery method as well. Everything makes sense.
Guided instruction, building on where students are and giving them an environment where it's number rich and showing them how they connect, and then building the precision and exactness as needed.
Right. I really appreciate that. I've got to go look that up now. But before we close, I'd like to know something about your own educational experience. You were a child prodigy, and I would like you to tell that story again when you were a wee child.
When I was on the potty.
Yeah.
I was just 2, I think. And I was sitting on the potty, and my uncle was sitting with me. And then I looked up at the ceiling, and I saw the heating coil. And I looked and I said, oh, hexagon. And
pretty good at an early age.
And my parents always told me that story, and they said, "Oh, this was really unusual."
Yes,
and I didn't realize how unusual it was till I had kids myself.
Yes,
and my kids are interested in lots of things, but hexagons at age 2 were not among the list.
You didn't repeat that story or anything.
Not on the list.
Now, I think you moved through a system, so you had to endure that, and most people, it was pretty rough?
No, what happened, and I think all you need is to be 1 year ahead. Mm-hmm. And then this feedback loop happened. So what happened is I was at least 1 year ahead. So when I got to 1st grade, they said, oh, you already know all this stuff. Why don't you you can just go work on whatever you want. So I worked on the 2nd grade math. By the time I got to 2nd grade, I already knew the 2nd grade math. Mm-hmm. So they said, oh, here, do the 3rd grade math. So while they were doing the teaching that brain damaged everyone in 2nd grade, I was learning 3rd grade math. Mm-hmm. And in 3rd grade, they said, okay, we're going to go brain damage everyone with our regular teaching. You can go do the 4th grade math.
But you were sort of like on your own.
So I kept doing, I was always protected from the standard math teaching just because I was 1 year ahead. And so then that just increased and increased because I wasn't crippled by the way math is normally taught.
And so you went ahead and did all of the mathematics and the physics both later on, and you did theoretical physics, but you ended up in math.
I was basically so. It's funny. I did theoretical physics, and I am an engineering professor now.
Yes.
And it turns out I teach all the courses that involve math.
Yeah.
So it turns out that all the things that I find very easy to teach, they all are connected by mathematical ideas.
I see.
And then I realized, oh, they're actually, this department, they're actually the same course.
They're
the same mathematics.
Yes.
We just give it a different name.
Yes.
We call it signals and systems here, we call it dynamics here, we call it circuit theory there, but it's actually one and the same thing. And if you can see that, well, then you've actually advanced, because
Right.
instead of learning 3 separate courses, you can learn one thing.
So the students are beginning to understand this thanks to your intervention
That's what
in this regard,
that's what I'd
right?
like to do.
Right.
So there's lots to do.
Yes.
So I'll never be
Evidently,
unemployed.
there is. Do the faculty support the idea too, or do you find academics are notoriously resistant?
No, I find-
sometimes. Are they okay?
No, Olin, for example, was founded to be a place of educational
Yeah,
change.
right,
So I
yes.
find a very congenial environment. And MIT, people are very flexible. They say, oh,
Yeah.
that's very interesting.
Try something.
Yeah, try. It's basically anarchist paradise over at MIT.
Yeah, that's interesting.
So there's always a skunk works here and there and
Yeah,
everywhere. So you
right,
can always try
right.
something. And people say, yeah, try it. If it works, let's do more of it.
Right, right. Well, that's cheering. But a word for Olin as well, too,
Yeah,
because
yeah.
they are experimental
Right, and they welcome that.
in this regard. I have to stop there so that you can talk to the
Oh, I'd be
people
glad
in
to.
the audience. And I thank you very much. It was very edifying.
I was interested recently how often mathematical insights or mathematical problem solving becomes a key for physicists to solve problems about order in the physical world. The mathematical insight speaks to it. And I wonder, so what is the nature of the intuition into order? What are they seeing that then that then speaks to the physical?
So why is it that the mathematical structures work so well for the physical world?
Yeah, what's the nature of what they're intuiting?
So I think it's, I have a sociological explanation for that, which is that until recently, mathematics and physics were one subject. So mathematicians, if you look, say, in the 1700s and 1800s, and you list all the great mathematicians, you can't, and then you list all the great physicists, you get the same list. Euler, Bernoulli, Newton, it was Newton who developed calculus, a mathematician or a physicist. Well, he developed calculus to study orbits. So maybe that makes him a physicist. So there was no separation. And it's only basically in the early 20th century, late 19th century that they started to split. And that's actually when mathematics stopped being so useful for physics. So it really was, people were trying to see what's the structure in the world and how can we explain it. And mathematics was the explanation for
What
that.
was Pythagoras after when he said everything's numbered?
Surveying. Well, so Pythagorean theorem was for surveying,
Surveying. Interesting.
but also astronomy. So the Greeks were fascinated by astronomy. And so partly they were looking at the structures in the astronomical world too, and their patterns of periods of planets in the sky.
But does that apply now to the whole this waves and quantum waves?
And string theory and all. Yeah, so that's actually, I think string theory is a further illustration of that point, which is, I think string theory is going to collapse at some point. It's a big ocean liner of thousands of different theories, and it hasn't yet produced what, as a physicist, you'd call a testable prediction, which is calculate the mass of an electron or a proton. Well, proton is a separate one, but say the mass of the electron. Right now, there's 20-ish different parameters in the physical theories, and we just have to put them in, sort of dial that number in, and we have no idea why that number is what it is, like how heavy the electron is. String theory, you would like it to explain some of these numbers, but it hasn't explained anything in that department at all. And people say, oh, well, the math is very beautiful. Well, maybe so, but it doesn't seem to have anything to do with the physical world. So I think string theory also illustrates the problem. It's the flip side of it. Once the mathematicians and the physicists are separate, then you start doing mathematics that has no relevance to the physical world. Yeah.
I've always felt that Einstein was more intuitive than mathematical. Didn't most of his relativity come long before he had the math?
Yeah, definitely. Actually, that's a really good example. So Einstein, for example, his special theory of relativity started, I mean, it's hard to know when anything fully started because these ideas start in the sort of back of your mind, but he describes it as starting from wondering what it would be like to ride on a beam of light. And that was just wondering about it. And then, so that became the special theory of relativity. And then he started to wonder, well, how do I connect this theory of motion with gravitation, with Newtonian gravitation, which had been around for, by then, 200 years. Because, for example, the special theory of relativity says that no signal can move faster than the speed of light, which is related to that moving on the beam of light. But in Newtonian gravity, for example, suppose the sun has some mass here and we have a field, a gravitational field. Well, in Newtonian gravity, if the mass of the sun changes, instantly we're supposed to feel the change in the gravitational field of the sun, and the Earth would change its orbit instantly. But Einstein said, well, that can't be true. That doesn't work with special relativity. How can I fit those two together? So, yeah, there's a bit of mathematics in there, but it really was a physical problem he was wondering about, an intuitive problem. And he figured out ways of melding them together. And so he was a great example of intuitive reasoning. And in fact, all to the end of his life, that was his objection to quantum mechanics, that it makes no sense.
He never believed in it.
He never believed in it. The math, he said, okay, fine, you can have your math, but it's physical nonsense. There must be something underlying it, underneath it, that gives you these probabilities. And I refuse to give that up. And I think he was right, and we're going to see more and more people pointing in that direction, saying, oh yeah, Einstein's intuition was right. Yeah.
To quantum mechanics?
Yeah.
That's interesting.
Yeah.
Yeah, I was reading something the other day about quantum teleportation.
Mm-hmm.
Can you talk about that a little bit? I'm still not sure.
I can't say anything sensible about it, so I'm sorry.
That and entanglement.
Yeah, and so entanglement is part of all of the way that quantum mechanics is thought of. And I think my view is with Einstein, there has to be a better way of thinking about it, which we haven't yet got to. So entanglement, I think of as actually what's really common there is that there's two different observers who happen to share some knowledge. And then we are mistakenly putting that into the system, but it's really states of knowledge in the observer. And people are starting to work out that way of thinking, but it's a newer way of thinking. It's related to what's now called quantum Bayesianism as well. But the old ways of looking at quantum mechanics are starting to crumble. And so I would even not put too much money on entanglement.
So that maybe some communication that actually does travel faster than the speed of light?
Not necessarily. So here's a way of getting things to seem like they travel at the speed of light, which is suppose we both we exchange a message, so we both know something, and then we go very far apart from each other. And then people ask me a question, do you know what's the answer to X? And I give an answer, and they ask you at the same time, what's the answer to X? And we both give the same answer. It would seem like that knowledge went faster than the speed of light because we're really far apart. But actually, where it came from is that we both knew it together, and there was some common kind of knowledge we shared for whatever reason. So I think we'll see more ways of looking at quantum mechanics like that, and not actually information traveling at the speed of light. Yeah.
You talked about the sky being blue.
Yeah.
Because of an electron on top of a piece of puzzle.
Of a proton, yeah, that's connected by a spring to the proton, yeah.
It's relatively new to me, I'm afraid. Could you elucidate it?
Sure. So what happens is the sunlight comes, and what sunlight is it's the representation of wiggling electrons in the sun. So the sun is really hot, and the electrons are jiggling up and down. And so one way we represent that is we say there's an electric field which is moving up and down. And so there's an electric field which puts a force on electrons, and also on protons, but they're so heavy they hardly move. So let's just take the electron. So the electron in the nitrogen atom moves up and down like this. Now, the sunlight has several colors in it. Let's say just two. Let's just take red and blue light. It's a mix of the whole spectrum, but let's take those two. So there's a red light, which is a slower jiggle, and there's blue light, which is a fast jiggle. And each of those jiggles radiates, so the slow jiggle radiates red light, and the fast jiggle radiates blue light from this atom. Now, the thing about the way electrons radiate is that the faster they accelerate, the more radiation they give. And it's actually a very steep dependence. So if you double the acceleration, you quadruple the amount of radiation. So because the blue light gives a faster jiggle, the acceleration is higher. and then for the slow red jiggle. So there's a lot more blue light coming off of these nitrogen atoms than red light, just because of the way radiation works. So the result is, as the beam moves through all the air molecules, it's coming along, there's this nice straight beam. So when you look at the blue sky, you're not looking at the sun directly. You definitely shouldn't look at the sun directly. You're looking to the side, and the sun is coming that way through the air molecules. You're looking at them this way, and they're radiating out of the beam. So what's coming out of the beam is more blue light than red light, because the blue light jiggles the electrons so much more, and then they radiate so much more. So you see much more blue than red, even though blue and red are, say, roughly in the same amount in the sunlight. So sunlight looks white, but what comes off it looks blue. And then you can check that this isn't total nonsense, which is there is a time when it's sort of okay to look directly at the sun. When's that?
When it first comes up.
Yeah, sunrise or sunset. So what's happening then is that now you're looking directly at that beam, which is going through a very long distance of the atmosphere, because it's just barely grazing the atmosphere. Here's the Earth, and here's the sunbeam going through, and here's you. So what's happening is all the blue light is being kicked out of the sunbeam, and what's left is the red light. So the blue sky and the red sunset are actually the same thing, and the red sunrise. Does that elucidate?
I'll Google it.
Okay.
I have to go back to Frank's book on optics. That's how far back I go.
Okay.
Where he discusses the blue sky, but he doesn't mention electrons and springs.
Ah,
Well,
it's
you're
hard.
calling it a spring, but I mean, it's just, the photon is it's putting out a blue photon as it jumps to different levels, right? Quantum levels.
That's another way of doing it, but you can also do all the quantum mechanics with springs. The math is the same.
People, I'm so sorry to interrupt. They want to get us, say something to him, and thank you so very much.
Yeah.
I really appreciate it.
Thank you.